Hello everyone. My presentation topic is improve the implementation and analysis of an algorithm to count graphical partitions. Thank you for being here. So this is an outline of the items we are going to discuss. Basically, we are going to talk about the partitions, integer partitions, graphical partitions, and the basic algorithm, Kohnert's algorithm, to count graphical partitions and how we improve this algorithm, and finally we present analysis of the algorithm and some experimental results. So the concept of partition is actually used in several different areas of mathematics. Here we are trying to talk about integer partition, which is used in number theory and combinatorics. So it is a very simple concept. So we have an integer, and we can express the integer as a sum of positive integers in several different ways. For example, 10 can be written as a sum of 4, 3, 2, 1. But you can also express it as the sum of 4, 2, 2, 1, 1. So there are several different ways to write the integer as sums of positive integers. And each list of these integers that sum to the given integer is called a sum of each list of these integers is called a partition of that given integer. For example, so we can say 10 has the partition 4, 3, 2, 1. Also, 4, 2, 2, 1, 1 is also a partition of 10. And note here, the order of the summands or parts does not matter. So usually we write the parts in decreasing order or increasing order for convenience. And different authors may choose different order, either increasing or decreasing. So graphical partition is just an integer partition whose summands or parts happen to be the vertex degrees of some simple graph. So I trust we are all familiar with the concept of graph from discrete mathematics, which consists of a set of nodes together with the edges between those nodes. So with such a concept of graph, we can introduce the concept of vertex degrees, which is the number of incident edges or neighbors of that vertex. So for any given graph, we can produce the list of vertex degrees. If we treat this list of degrees as an integer partition, then we can talk about graphical partitions, which is just a partition that is a list of degrees for some graph, simple graph. But turns out that not all integer partitions are graphical partitions. Only some of them are. And also, since the degree sum of a simple graph is always even, then only even integers have graphical partitions. So in the literature, we usually use the function Pn to denote the total number of unrestricted partitions of n, and Gn to denote the number of graphical partitions of n. That's our basic notation. So there are a lot of decision algorithm, enumeration algorithm, and counting algorithm regarding partitions and integer partitions. So for example, if we want to test whether a given integer partition is a graphical partition, we can use the Elders-Galai criterion or the Haver-Hakimi criterion. And in fact, there are several other equivalent criteria. All these can be implemented as efficient algorithms. And if we want to generate all partitions of given integer n, we also can use some efficient algorithm to do that. Notice that the function Pn itself grows very fast. It grows exponentially. So for large n, usually it's not very practical to generate all these Pn partitions of n, but we might be interested in generating a small number of random partitions of n. And some authors actually have done some research in that area. But notice that we don't actually have to generate all partitions of n to get the function value for Pn. There are additional algorithms to count or compute the value of Pn itself without having to generate all Pn partitions. So such algorithm would be very efficient. We can actually use just a personal computer to calculate the function value for very large values, for like 10,000s or even larger. And the beautiful result from mathematics is that we can compute an approximate value of Pn. Here is the formula. It's actually Pn is growing like exponentially e to the pi to the square root of n, something like that. It's very fast. The function value grows very fast. So if we only actually want to calculate the approximate value, we can use this asymptotic order without resorting to an exact algorithm. And this result can be proved using analysis. In fact, there's a related result to express the function Pn as an infinite series. That would be a more complicated result, so the formula will not look as concise as this one. So we have talked about how to generate unrestricted partitions, but if we want to generate all just graphical partitions for a given even integer n, there are also algorithms to do that. For example, Barnes and Salvage algorithm. That is a beautiful algorithm that can run in constant amortized time, a very beautiful algorithm. But if we want to just calculate the function value Gn itself, we do not have to actually generate all graphical partitions of n. For example, we can use Barnes Salvage recurrence space algorithm or Kohnert's recurrence space algorithm. Our improved algorithm actually is based on Kohnert's recurrence space algorithm. We're going to talk about that a little later. So these counting algorithms can calculate the function value Gn without generating those graphical partitions of n. Unfortunately, we cannot or are unable to derive the asymptotic order of the function Gn itself right now. We only know some upper and lower bounds. In particular, we know compared to the function Pn, Gn grows relatively small. The ratio is approaching 0 when n grows large. But we do know that the function Gn itself still grows exponentially fast, and seems that not much research has been done about like generating a random graphical partition when n is large. Yeah. So Barnes and Salvage's algorithm to compute the function of Gn based on their recurrence, which is the four-variate function Pnkrs here represented. Their algorithm to compute Gn has a time complexity of n to the power 4, and space complexity is cube, n to the power 3. And using this algorithm, they compute the function value up to n equal to 220, but that's like more than 2 decades ago. Nowadays, we can compute larger value using their algorithm, although it's still time-consuming and also it costs a lot of memory. And their function, this four-variate function Pnkrs satisfies the recurrence like this. It's a somewhat complicated recurrence, and with the setup of proper initial conditions, we can calculate the function value for any of the 4 inputs nkrs. And based on their theory, they can calculate the function Gn as this Pnnn0. It's a very concise formula and also beautiful. But unfortunately, we cannot get the asymptotic order of Gn based on this algorithm. And to this day, it's just still an open problem. And Kohnert's algorithm to compute the function of Gn is also based on a 4-variate function, but the idea is quite different. And they can, and at the moment of publishing their paper, they can compute the value of up to more than 1,000. That's quite impressive. And the idea of Kohnert's algorithm is to express the partition each given partition of n into 3 parts. So for example, if we say the partition is lambda, then lambda can be expressed as the 3 parts: L lambda, M lambda, R lambda. I think it represents the left side, the middle part, and right side. These 3 parts are centered around the Dufy square of this partition. And they have this kind of relationship for their weight. Here is the weight of each partition, like lambda, L lambda, M lambda, and R lambda, and just the sum of the parts of these partitions. And turns out the previously mentioned criteria to test whether a given integer partition is a graphical partition can be transformed into equivalent criteria here, represented as L lambda is L lambda dominates R lambda. That's the sufficient necessary condition to say that the partition lambda is a graphical partition. So in order to calculate the function Gn, we can classify all these graphical partitions of n into several classes according to the Dufy square size. So we can use Gin to represent the number of graphical partitions of n with given Dufy square size I. So based on how the lambda partition can be expressed as 3 parts, so we can just count the number of pairs of L lambda, R lambda that satisfy this dominance relationship. L lambda dominates R lambda. Because based on that partition, we know that the middle part, M lambda, it must have a weight of I times I minus 1. So at this point, if we define a 4-variable function P, M, K, N, L, the meaning is this is number of pairs of partitions, mu and v, such that they have this relationship. The weight of mu is m, the weight of v is n. The number of parts of mu and v are k and l respectively. And we find that Gin, the function, the number of graphical partitions with given Dufy square size I, can be expressed using this formula. And of course, since a given partition of n will have a Dufy square size from 1 to up to d, where d is the largest possible Dufy square size, then the final formula for Gn is like this. So we only need to calculate the function P, M, K, N, L for arbitrary inputs. Then we are able to calculate the function value Gn as a finite number of these function values. And to calculate the function P, M, K, N, L, we can use several recurrences. Kohnert gave us 3 recurrences. We actually just need to use 2 of them listed here. The third one can actually also be used, but it won't affect the time complexity. So our improvements in the first part is a more precise formula for the value Gin based on some observations, how some of the entries in the original formula are actually 0. So we can discard those. And also we give a more precise value for the largest possible Dufy square for any graphical partition, which is the square root of n minus 1 in case n is greater, according to whether n is greater than d times d plus 1. So as we said, Gn is just a finite number of these function values. So as long as we can compute these function values, P, M, K, N, L, then our job is done. So how do we do that? We just allocate a 4-dimensional table to hold all these necessary function values. And once we have these entries in the table, then we pick those that are needed to compute the function value Gn from that table. Then we're done. And we carefully analyze how large a table we need to allocate to hold all these needed entries. And we find that we can use the regular array allocation technique from computer programming to reduce the number of entries needed in the table. And the idea is that we find that the allocation size for the first 3 dimensions of the function actually can be made smaller and dependent on the index of the last dimension. So that's that's the technique we use to reduce the table size from half of n cubed to about 2/15 of n cubed. So about 1/4 of the original table size. And we also use the dynamic pruning technique to fill in the table entries in an optimized way so that most of the entries of the table can be filled in within constant time using the previously mentioned recurrence. And only a small number, which actually is no more than a constant number of n squared entries from that table, need to use non-constant time. But still, we managed to fill in those entries with O(n) time per entry. So we can calculate the time complexity is O(n) cubed. Yeah. So this is the complexity analysis. One of the major contributions of this paper is we can prove the time complexity is O(n) cubed, which is the first such algorithm that can compute the function value Gn. And as we said, we use the 2 of the 3 original recurrences satisfied by the function Pmknl. And the third one can also be used, but it won't affect the time complexity. And after the entire table has been, the 4-dimensional table has been constructed and filled in, we can just choose a small number of entries from that table to sum the Gn value. And we find the time complexity is n cubed and the space complexity is also n cubed. But notice we must use the dynamic programming technique to fill in the table and sum the entries to get the Gn value. Without the dynamic programming, we cannot achieve this time complexity. And the previous best time complexity is O(n) cubed from Barnes and Salvador algorithm. But the space complexity of these 2 algorithms are the same. So here we present some experimental results. With the general support of XSEDE, we use a supercomputer to compute all function values up to 12,000. The number of graphical partitions of 12,000 is about on the order of 10 to the power 116. It's quite a large number. And here we also listed the time performance comparison of the 3 algorithms: Kohnert's algorithm, Barnes and Salvador algorithm, and our improvement to Kohnert's algorithm. But you can see Kohnert's algorithm is actually implemented more than a decade ago, so the time is not compared to the other 2 times, which is tested in just the recent years, early 2020s. But anyway, our algorithm demonstrated a bigger performance boost. It only needs 2 seconds to compute the function value of 760, and it uses less than 1 GB of memory. So it has an advantage in both runtime and memory usage compared to the previous algorithms. So future research directions. The first is we trust our 4-dimensional table has already been quite optimized, but we cannot prove that is the smallest possible table that can be allocated to compute the function value. Maybe there's additional room for improvement. But we also try to find if is there any better idea or different idea to compute the function value Gn, or any of those algorithms to compute the exact value of Gn can be used to derive the asymptotic order of Gn, since we are also interested in the asymptotic order of Gn, because such an order can be used to compute an approximate value of Gn in a faster way. So here's our list of references. Our paper lists more references if you're interested. I hope you enjoy this presentation. If you have any questions, you're welcome to contact me. I would be happy to answer any of your questions. Thank you.